In this video, we will talk about a variant of Byzantine agreement called Approximate Agreement, and we will see how to solve it in a synchronous network. We will be looking at a setting of n nodes in a network. Out of these nodes, f are Byzantine. Each correct node has a real value as input. As the name suggests, approximate agreement will enable the correct nodes to agree on a value, up to a predefined error epsilon. This error can be arbitrarily small, as long as it is greater than 0. This is the epsilon agreement property, which requires the correct nodes to output values that differ by at most epsilon. Approximate agreement will also ensure that the outputs of the correct nodes are meaningful or valid. The validity property that approximate agreement considers is correct range validity. Correct range validity requires the correct nodes to output values that are within the range of their inputs. If the correct inputs are between 0.25 and 0.75, the correct nodes may only output values within 0.25 and 0.75. So far, we have learned that approximate agreement requires the correct nodes to output, for any predefined epsilon, values that are epsilon close and that are in the range of correct inputs. We will now be looking into how this problem can be solved. We will see a synchronous algorithm achieving approximate agreement when the number of Byzantine nodes is lower than 1/3 of n. The nodes will first distribute their input values. This will enable each correct node to see the n-f correct inputs, plus at most f values from the Byzantine nodes. A possible strategy of the Byzantine nodes will be to send values that are way too low or way too high, as an attempt to push the values that the correct nodes may want to output outside the correct inputs range. To prevent this strategy, the correct nodes will discard the outliers. Concretely, they will discard the lowest f and the highest f values received. This way, all values remaining are guaranteed to satisfy the correct range validity condition. Moreover, since n is greater than 3f, at least one value remains after discarding. Then, each node will compute its new value as the average of the lowest and the highest values remaining. This will halve the range of values held by the correct nodes. To see why this is the case, we first need to observe that the correct nodes end up with at least one value in common after discarding the outliers. Pause the video for a moment to think why this is the case. First, recall that every correct node receives the n-f values sent by the correct nodes. Of course, some correct nodes may also receive up to f values from Byzantine nodes. Then, each correct node discards at most the lowest f and at most the highest f values that were sent by correct nodes. This means that at least one correct value is never discarded, and this is a value that all correct nodes will have in common. Now, we know that all correct nodes have some value in common after discarding the outliers. And recall that they compute their new values as the average of the lowest and the highest values remaining. Pause the video for a moment to think why the range of values held by the correct nodes gets halved by using this strategy. The strategy we used for computing the new values comes down to computing the midpoint of the interval between the lowest and the highest values remaining. In other words, we are computing the midpoints of intersecting intervals. The distance between these midpoints is at most half the size of the interval's union. In addition, each of these intervals is included in the range of correct inputs. This is guaranteed by the step where the correct nodes discard the lowest and the highest values received. Then, the distance between these midpoints is at most half the length of the correct inputs range, and therefore the range of correct values is halved. So far, we have an algorithm that enables the correct nodes to obtain closer values that satisfy correct range validity. On the other hand, epsilon agreement is not yet achieved. We will run this algorithm multiple times, or for multiple iterations. In each iteration, the correct range validity property is maintained, and the correct values range gets halved. This ensures that, eventually, epsilon agreement is also achieved. The next question is, when exactly is epsilon agreement achieved? Assume that the inputs of the correct nodes are between two values A and B. Pause the video for a moment and compute how many iterations guarantee that epsilon agreement is reached. A sufficient number of iterations is given by the base 2 logarithm of b minus a divided by epsilon. After this number of iterations, epsilon agreement is achieved, and therefore we have solved approximate agreement. The algorithm that we have discussed is secure as long as f is lower than 1/3 of n. But is this optimal? Or could we tolerate more Byzantine nodes? Pause the video for a moment and think about it. The condition that f is lower than n divided by 3 will be necessary. The argument for this is very similar to the impossibility results of Byzantine agreement. We may look at 3 nodes. A correct node with input 0. A correct node with input 1 and a Byzantine node. The Byzantine node will act like a correct node with input 0 towards the correct node with input 0. It will also act like a correct node with input 1 towards the correct node with input 1. The correct nodes do not know which other nodes are correct. But, from their perspective, if the Byzantine node is actually correct, they have to output their own inputs due to correct range validity. Then, the outputs of the correct nodes will be 0 and 1. By trying to achieve correct range validity, we broke epsilon agreement for any epsilon lower than 1. This means that f must be lower than 1/3 of n in order to achieve approximate agreement, and, therefore, our algorithm achieves optimal resilience. In this video, you have learned about approximate agreement. This is a variant of Byzantine agreement that requires the correct nodes to output epsilon close values that are in the range of correct inputs. You have seen a synchronous algorithm achieving approximate agreement when f is lower than 1/3 of n, and you have also seen that this condition is necessary. Thanks for watching this video.